Java on the main image. Isn't that much I think we have? Good morning. Good morning.
Hi.
I heard arctangent.
Oh, yeah.
Solution of an irrational integral.
We're supposed to solve y-hand the integral between 0 and tan 1 of x arctan 3x.
Oh, that's right on. Yeah, those irrationals, you just have to know what their values are. Most of those are very difficult to do substitution to solve.
He did it in class and took 3 pages.
Yeah. Not the easiest thing, which, again, if you want to memorize the process, it's good for a mathematics major just to do so, because you end up doing so much of it, but not particularly practical if you're trying to study for an exam, for instance. And engineers never use stuff like that, nor do GIS individuals. So it's that's an amazing issue that we have in physics, and mostly physics these days. It used to be people that piled into physics, especially calc-based, were either primarily hardcore engineering majors, or physics majors or chemistry, in which case you just focus on sort of the traditional approach. But now with such a broad geology, some of these other areas, it just self-defeats pre-med. It's very difficult to approach a subject in a practical way that is useful for everybody. Nonetheless, we have some discussion of optics today, and bless you. So I want to focus on two-lens problems, and then we'll extend two-lens problems to how optics works for the human eye. So it's a nice organic location, and the eye is a beautiful optical system. The way it works. So I'm just going to write the basic relationships down, just sort of the key ideas that you always use for any lens system. I'll just call these the key reference nodes. And those key reference nodes are really remembering how to use the principal rays to identify image location from an object. So you always have to focus on how we use principal rays as they're related to an object-image relationship. We've done some of that. It's in some cases easier than others. Then we have the working relationship, which is the thin lens equation, or if you will, because we use it for mirrors as well, it's probably easier to think of it as the image formation. Equation. And the idea then is if you take 1 over the object distance plus 1 over the image distance, if you add those together, you should get the inverse of the effective focal length for that particular lens. And then tangentially associated with that is the general relationship of magnification. And more often than not, we're usually looking at dimensional or height magnification. And height magnification is related to the effective image height divided by the object height, which is also related to the ratio of the image distance to the object distance. And there's a minus sign, because when you have real images, the image height is inverse or upside down. So it's really in a dimensional sense or in a directional sense. It's a negative quantity. So you gotta have a little minus sign in there, just to keep track of reference. So maybe we'll just call this lateral magnification. angular magnification. And if we have time, we'll get to that. But these are sort of the key ideas. So everything we do is just kind of like with Newton's second law. It's just sort of an iterative application of these basic ideas. So to this end, let's look at a simple lens system. And I'm going to start by looking at what happens with the image formed by an object for one lens. And then we'll add a second lens to it and just sort of see what happens when we do so. Sort of the best way to approach it. So you have a lens. And I'm going to call it one, so we'll have two lenses eventually. And for this particular lens, let's assume a focal length of plus 50 centimeters, or 0.5 meters. So I'm going to then identify the two focal points associated with that lens. So we would have F1 and F1 prime. And we'll put an object out here somewhere. And we'll make the object distance 70 centimeters from the first lens. Doesn't matter, I'm just trying to think of a good one that will give a decent secondary image.
What's the height of it? Do we care yet?
Yeah, don't really care yet, but might as well give it something. So how about 0.1 meters? Now, once we start talking about real, physical dimensions for what we see and what we observe, it's usually better to use SI units. But typically with lenses, because of the range over which they're useful, we oftentimes talk about them in centimeters, which is not a good idea, but it's just traditional among other reasons. Okay, so we have an initial height of object 1 of 10 centimeters. So we can do the calculation, but maybe we'll just start by identifying approximately where we would expect this image to be formed. So I'm going to draw some principal rays. So ostensibly, we would have an image formed somewhere out here. From the information given, we can figure out the numbers. So that would sort of be the basic ray diagram. Now, to calculate the information at hand, you might say, well, the location of the image. I1 would be related to the inverse of F1 minus the inverse of O1. I take the way, 1/f, another way of describing 1/f, you remember what we called it as a sort of secondary naming? 1 over the focal length for any lens. That's the optical power of that lens, another way of thinking about it. The nice thing about optical power, the bigger the 1/f, the more the lens bends light, which is sort of a little more intuitive than the smaller the focal length, the more the light is bent. You know what I mean? It's just the stronger the lens, the larger the value, so 1/f is sometimes helpful to think about. But regardless, we have the inverse of 0.5, which would be 2 centimeters, or 2 inverse centimeters. And I don't want to do all this math and do that all these little pieces, so you can tell me what that is. Calculate and take it down. Again, helpful hint, you use the inverse button, you won't get yourself mixed up. So if I were going to do this, I'd take parentheses, and I would say 50 inverse minus 70 inverse, and I put the other parentheses, and I do an inverse again. And that tells me it should be at about 175, which tells me my ray diagram is skewed to hell.
Nah, I tried to get all precise with it, and it's way to the end of the page.
Yeah, I sort of made a little arc here. I think I'm going to try to correct it because when we put that second lens in here, it would be helpful. So you don't have to change anything in your notes, but
5 over.
I just have to make a semblance of an effort to get that out there. And principal rays 1 and 2 are usually the easiest to deal with. At least if you're not using a straight edge. If you're using a straight edge, then principal ray 3 is always nice because it's just one line. Look for the intersection of any of the other. If I were able to. It's amazing how even when I'm off scale, all my lines always seem to converge perfectly. So there's HI1, and this distance would be I1. That's still not good, but at least it's closer to what it ought to be. It's still a little bit off. Part of the reason is because this F is probably needs to be a little bit further over. We'll just deal with it though.
Well, your height of 10 centimeters is twice about what you
It doesn't, the height doesn't matter. I mean, from a scale perspective, it doesn't look right, but from the identification of where the object and the image are, it won't matter. Because you don't actually use the height to calculate where the object and image are, per se. But the bigger this is, the more room there is for skewing, just because it's going over a wider space. So, practical engineering issue. Speaking of which, there's another example, I guess it's kind of related to this, that is sort of counterintuitive. Turns out when you play video games, you perform better on smaller screens than you do larger screens. The same video game. Doesn't matter if in my day it was Missile Command and Pac-Man. Now it's Minecraft, or, well, I guess Minecraft doesn't matter. SOCOM or Call of Duty or whatever those games are where you're moving around. The reason is the smaller the screen, the slower things appear to move. The larger the screen, things are going back and forth, and it, even though angularly it's the same, it affects your perception. So it actually, you're doing things in instant replay almost, in a slow motion when you look on a smaller screen. Of course, you can't see the details as well, but in terms of maneuvering, it's actually easy. When things are coming at you, it's easier to react. All perception. Okay, so nonetheless, what did we end up here with? 175 centimeters? So you always try to do your best with your ray diagram. What's more important is the relative information, and in this case, inverted outside of the focal length, actually more than twice the focal length distance away. And of course, the image is much larger than the object. So it gives us a reference for that information. Now, if you wanted to figure out the height, then by using the relationship of magnification, we would say, okay, we've got to take the original object size and then multiply that by the ratio of negative I to O. That number's almost 3. No, 2. Based on that, object image 170, yeah, a little over 2. So we'd expect the object to be twice the size of the image, or the image to be twice the size of the object. N inverse 2.5. So 2.5, or the ratio is 2.5. So the answer would be 25 centimeters.
Yeah.
0.25 meters. Nothing like mixing and matching meters for me. I can't see that. Oh, look at that thing. Leave that up there like a rational human being. I should be able to never have to look for it in principle. Okay, now that's the easy part. We've done a lot of that. And of course, with real images, with positive focal length lenses, that's about as easy as it always gets. Calculation makes no difference, but it certainly makes it easy. Now, let's look at two cases in terms of an image formation when we put a second one. And I've got two, well, I can put it in many places, but just for the simple first case, well, I'm going to go ahead and put H1, image 1, over here, negative 0.25 meters, just so I've got the information. Now I'm going to do, you can put a lens over here, so that's 175 centimeters. For the hell of it, I'm going to put a lens over here at let me make sure this is reasonably accurate. This is supposed to be 175. So let's call it 200. So over here, I'm going to put a warp lens at a distance of 200 centimeters away. Now, there's all a million possibilities for these types of problems, but I'm going to, for now, I'm going to leave it there. And why don't we make this lens have a focal length? For now, let's keep it similar to the first focal length. So let's make F2 have a value of plus 50 centimeters. And the question now becomes, where is the final image? And what is its size? So here's how you approach the problem. Once we know where the first object is when it's formed, or first image, excuse me, that becomes the object for the second lens, right? Because that's what we're trying to do. We're trying to take the image from the first object, or from the first lens, and then look at that image to the second lens. So, first of all, let me put this stuff in here. So this would be F2 prime, and somewhere out here would be F2. Now, here's the thing, and this is what makes life easy. Once you know where this object is, or this image is, to redetermine, maybe I should just call this image. That becomes the object for the second lens. So now, we don't have to look at anything to do with that first lens ever again. Once we know where that first image is, that's the object now we're looking through with the second lens. We don't have to worry anymore about it, so let's just get rid of this altogether and figure out what this object looks like through the second lens. I'll leave the second lens up there for now, but I'm not going to deal with this. Okay, so now we play the same game. And hopefully I'll have enough room on this board. If I don't, then at least I can kind of eyeball where it is in the calculation. So if this distance is 200, and this distance is 175, I'm going to have to put this over a little bit more. I got to move these things a little bit. It's not quite to a good scale. The distance from here to here should be 50. Or I'm sorry, it should be halfway between. And so let's scoot everything over just a touch. Again, usually is better if you can do this to scale. So now we know that O2 is 25. This is 25 centimeters. And this is 50 centimeters, right? So we just need that information. So now we can say that O2, image 1 becomes object 2. As complicated as things start to look at the beginning, once you erase the first, everything about forming the first image, you don't have to worry about it anymore. It's just now a regular optics problem with one lens. So all we have to do is figure out where this gets formed through this lens. And again, the observer is presumed to be over here. So, I'm going to draw the principal rays. One ray is going to come in like that. One ray is going to come in like that. And the third ray, ray 2, is going to come in something like that. So with any luck, I'll kind of stay on the board, but it's going to be tough. It doesn't matter what the lens dimension is, because the principal rays aren't always real. That's the key to take away. We use it as a reference, but they don't necessarily, geometrically, they don't have to be real. They just allow us to identify. Because all the other rays inside that are happening, remember, this guy's producing rays in all directions. It's just not, they're not all useful to figure out where the image is going to be formed. So we're just trying to do best we can. So we just will extend our lens so that we can use it. Now, all of these rays, when they come through, this ray is going to come out parallel. This ray is going to go like that. And this ray is going to go something like that. Hopefully, I don't know if he's going to come close enough to scale, but we're going to have to deal with it. The problem is, no image is going to be formed over here. There's not going to be a real image formed by that last lens. The reason is all the light that comes through diverges because the object is inside the focal point of the second lens. If it were outside, we'd know at least we'd get a real image so we'd know where to look for it. We don't have that opportunity here. So we have to draw the virtual rays and trace backwards. Without doing anything else, I can at least establish it's going to be a virtual image, a final image. So, you where it is. But our final image, I2, is gonna be somewhere outside of F2. I don't know for sure if it's gonna exceed F1 or be, further over. I just know it's gonna be somewhere outside of this.
It's right on it.
On F1?
On F2 prime.
F2 prime.
It's at negative 50.
Yeah, it's right at 50 centimeters.
Is it really the final
Yeah.
image?
Mm-hmm.
And it's half a meter tall.
That's about a good
So if I drew these lines straight, it'd end up right here, huh? That's cool. So if I hadn't tried to fake it so badly, I would have probably ended up where I was supposed to end up in the first place. Isn't that funny? What I get for trying to cheat.
But you had that nice straight edge to work along there.
I know,
Too bad.
I know. Well, that's what I was kind of hoping for. I was hoping to get that straight edge, make life a lot easier. So I got to get rid of this now because I got to be able to look down here. So in principle, then this would be object type 2, and the final image would be tip. So in spite of my crappy diagram, what's important to take away is that I just do the same image formation process for the second way. There's nothing fancy here, there's no magic or even deep mathematics. Just do the same thing again. So to find the final image, if I were going to do the calculation, I would say I2 would be the inverse of F2 minus the inverse of O2. I got to take the inverse of that. And negative 50 centimeters. So HI2,
Shouldn't it just be 50 centimeters though, because isn't the positive side on the left side of the lens?
no, it's on the opposite side of the observer. So it's going to be a negative. And if you did the calculation, because O2 is, now,
Well, 1/50th minus 1/25th makes sense. Negative.
yeah, so it's twice, 1 over O is twice 1 over F. Yeah, when you're looking at inverse relationships in the denominator, everything is backwards because you got to do the relational, one's bigger than the other, so it's larger, but then it's larger in the denominator, so that makes it smaller, or vice versa. So to get HI2, we would take HO2. Oh, look at that, we got water here. No, not water, it's hydrogen dioxide, it's backwards. Multiply it by negative I2 divided by O2. Which would be, we said it was 175 originally? No, it wasn't 175, it was 2.25. So we had 0.25, and it's a negative, by the way, it's upside down. And we multiply this by a negative 50, divided by 25. So these negatives cancel out, but we're still left with a negative, which is good, right? Because the final image is going to be inverted to the original object. So it should be negative 0.50 centimeters. So what can we say about final image inverted? And calculations were done correctly. It's about 5 times the original object size. Take this and 1, 2, 3. There goes my scale to hell. true magnification of this process. Or if you will, let's just call it the net. It's lateral because we're not talking in this particular time about angular anything. But the net lateral magnification. Well, the easiest way to do it, this is always the case, m net will be equal to the image height divided by the original object height, right? That's functionally, that's what it is. You got something you're looking at, it's gonna be bigger or smaller, so, and you're gonna see it in a certain way, so what's this value? We have negative 0.5 divided by 0.1. The meter units cancel out anyway, and we get negative 5. So in principle, the actual image is 5 times the original size of the object. Or this is 5x, but it's an inverted 5x. When you look through a microscope, by the way, you're looking at an upside down image. And typically with refraction telescopes, the same thing. This is why when you go to move it, you got to move it backwards. Have you ever used a nice telescope and tried to look at something, I don't know, it could be a star, but even like a planet, with a really nice manually operated microscope, or telescope, excuse me? When you have to adjust the X and Y because you're not in position, because of the rotation of the Earth and any relative rotation of the planet, when you're looking at something under high magnification, when you look at it, it goes by. You find it and then it's gone. And so you have to adjust it, but you have to adjust it backwards. Because the image is upside down.
And chase it along.
And chase it along in order to see it. If you don't have a nice GPS, computer-controlled focusing system, which makes life easy because you just sit it up there in the latitude, longitude, it knows how fast you move, and it just finds it. But yeah, I can't even imagine trying to do that in the old days like Galileo did. With any decent telescope, it's just...
Didn't Galileo just do this?
Yeah, he did that. Well, he wasn't looking at magnification, so he was just up there doing that. Yeah, and if it's on a tripod, you can just kind of move it, whatever's the way, just follow it. But yeah, it's backwards. So it's just screwy. Okay, so any questions on the process? I might also ask just